Okay, so these were the quantum selection rules, and as I was explaining to Claudette, they are not hard rules. That is, they can be disobeyed because we do not have the molecule in a vacuum, we have the molecule in a solvent. And so the system can interact with the solvent molecules, and we can, for example, change the spin from a singlet to a triplet by, for example, interacting with an oxygen molecule in its spin triplet ground state, which could be in the water, in the solvent, for example. So these are only partially obey these selection rules, but they give rise to different probabilities, to the possible interactions which can occur. So now I'm going to talk to you about the possible photochemical reactions. So what we have then is a molecule which is in its ground state, absorbing a photon and going to its first excited state. And this could give rise to a photochemical reaction to produce a new product, for example, which has a rate constant, let's call it Kr for the reaction. Or it can go through another rate constant to intersystem crossing. That's when we go from the singlet to the triplet state, triplet excited state. And that can give rise to phosphorescence, for example. Or it can also go through internal conversion directly to the ground state again, which is S, singlet, ground state. And that is what most of the fundamental molecules in their final configuration, when they have been finally optimized for dissipation, that is what they're doing. So this has the greatest rate constant usually for these fundamental molecules. Or we could also have fluorescence, where we go to the ground state from the excited state through the emission of a photon. So to define these probabilities, they can be different. So we call that quantum yield. So the quantum yield is just the number of molecules undergoing the reaction of interest. It can be any one of these reactions. We can have not only one reaction here, we can have many different photochemical reactions going to many different products. Okay, so the number of molecules undergoing the particular reaction of interest over the number of photons absorbed by the substance. The number of photons absorbed by the substance, we call that W. Okay, or actually that is the rate. So this is in terms of numbers of photons. And we can also have it in terms of number of photons per unit time, which is the rate. So for example, phi can also be defined as the rate of the reaction of interest over the rate of light absorption by the photoreactive substance. And that rate of light absorption is defined by W here. So you can imagine we have a system in a solvent, molecules in a solvent under light. And at the beginning, we're going to have different reactions occurring, but eventually we'll come to a stationary state in which the number of excited molecules stays relatively constant if the flow of photons over the system is constant. Okay, when the chemists write these square brackets, they're referring to the concentration. So this is the concentration of the singlet excited state. Okay, so in the stationary state, it will go to 0, and the stationary state then is just defined as the number of the rate of the light absorption by the photoreactive substance minus these different rate constants for the different possible reactions which could occur: reactions, chemical reactions, photochemical reactions, or intersystem crossing, internal conversion, fluorescence. Okay, so you can convince yourself that this is the right equation, and then if we want to get the rate constant for a particular reaction R, so that's K sub indice R. We just solve this equation for K sub indice R times S star, the concentration of the excited states, over the number absorbed. And from this equation in the stationary state, we can show that that is just equal to Kr, which is the rate constant for the particular reaction over all the others. So the sum of all these quantum yields has to be equal to 1. And as I mentioned, we can have much more than just one particular photochemical reaction. We could have P1, P2, P3, so on. Okay, so
what is W?
Yes. Sorry?
What is W in the
W is the rate of light absorption of the photoreactive substance. So it's the rate in which we're absorbing photons in the substance and causing it to go to the first singlet excited state.
Okay.
Okay, so now for looking at internal conversion, remember this is a photochemical reaction. It's also considered a reaction that we are interested in because this is dissipation. This is going from the excited state to the ground state through vibrational dissipation. Okay, so that's what we're looking at here. And this is what is known as a conical intersection. It's in terms of coordinate of the nuclei, okay, the atoms in the molecule. And this is only a schematic diagram because really, you know that we have 3n minus 6, mixing Spanish with English, 3n minus 6 degrees of freedom for a molecule which has n atoms. Okay, and the minus 6 comes about because of the rotation and translation, which have to be subtracted, these degrees of freedom. So a molecule moving, constant velocity or rotating, those degrees of freedom we remove for the excitation, looking at the excitations. So we have 3n minus 6 for a three-dimensional molecule. For a two-dimensional, we have 3n minus 8. But I won't get into that. So what this is showing is that this is the ground state, electronic ground state, okay? And these are the vibrational states superimposed on the ground state here in blue. So we get a photon which brings the system from its ground state, electronic ground state, to its first electronic excited state, which, as I mentioned, is usually the singlet state. But now, it turns out that for some of these molecules, what happens is that when it's in its excited state, the minimum can actually be a different geometric configuration than when it's in its electronic ground state. So this is, we know this is adenine, it's planar in its electronic ground state, but in its electronic excited state, the minimum corresponds to this coming out of plane of this carbon atom. So this carbon atom here comes out of the plane, and that gives us a different vibrational spectrum. So it can go to lower vibrational spectrums, and they can actually intersect with the vibrational spectrum superimposed on the electronic ground state. So this is here in blue. So at this point here, this is known as the conical intersection. So this allows us to go from electronic excited state to electronic ground state very rapidly through dissipation, through vibrational motion of the molecule. And eventually the vibrations go into the solvent. So through hydrogen bonding into the water molecules, for example. Okay, so this is a conical intersection which allows us to go to the ground state, or what is known as internal conversion, very rapidly in picoseconds. But we can also have conical intersections which lead not to the ground state, but to a product molecule. So we go to a different molecule, we can transform this molecule, and it becomes something else, not adenine anymore. So we have also these conical intersections to these photochemical reactions, to the P's, which were listed here, so to these ones. Right now we were only talking about internal conversion, but we can also have conical intersection to these other reactions. So then the conical intersection can lead to the ground state through internal conversion. It's rapid dissipation of the electronic excitation energy or into a new product. And what defines which way it goes to the internal conversion or to a different product depends on the quantum efficiencies for those. As I mentioned in the previous slide, we determine the quantum efficiencies for those possible channels or different reactions. So, for example, the case of conical intersection to the ground state for adenine. So when we excite the molecule by a photon, which is represented by this blue arrow going up here, we go to an excited vibrational state on the first electronic excited state. And it's usually the singlet state. And then we get dissipation with vibration, which allows us to go through this deformation here into a new configuration. So we deform the potential energy surface because the electrons are now in another orbital, an excited orbital. That causes a change in the configuration. So this is not really the Franck-Condon principle. This is called the Franck-Condon region, where the molecule still has the same form as the molecule in the ground state, but very quickly it can deform itself, go out of plane, and this provides it with a new set of vibrational excited states on the first electronic excited state, which connect in energy with the vibrational states on the ground state. So this allows us to go very quickly to the ground state from the first excited state. And this is internal conversion. And this is in case picoseconds for adenine.
Professor,
Yes, Claudia.
why does the reconfiguration, the change in the geometric of the molecule allows well that change into the vibrational mode? Why this changing of geometry makes easier this electronic to vibrational?
Yes, because as long as we have a degeneracy, for example, if we didn't have this out of plane motion here, then we wouldn't have the potential energy surface changing in this form. This is for the excited state. It would remain here. So there would be no overlap of the vibrational states. But because it changes its form, it's going out of the plane here. So we get new vibrational states, which were not in the original ground state, no, in the ground state geometry in the Franck-Condon region. And that allows us, because of this degeneracy in energy, that we can go from the electronic excited state to the electronic ground state through vibrational dissipation. Okay, so you have to imagine that when the configuration is in this form, okay, these are the nuclei, the atoms. When they're in this form, they have a certain distribution of vibrational states superimposed on this first electronic excited state. But when it goes out of the plane, this atom goes out of the plane, then we have, so this corresponds in fact to the proper electronic excited state when it gets deformed. And this is in fact the ground state of this deformed state, but we can go through this to lower energies. These are the potential energies until we get to a crossover point with the ground state. So when we have a degeneracy of energy, we can go from these vibrational states of the electronic excited state to the vibrational states of the electronic ground state, and rapidly to the electronic ground state. Okay. What you have to think about is that we have different set of vibrational states which are superimposed on the first excited state, and the first excited state gets deformed. Its potential energy gets deformed by one of the atoms coming out of the plane. So it takes on a different potential energy surface. And these two potential energy surface, the ground state and the excited state, they can overlap and they can connect. And that allows us to go very quickly to the ground state. Okay.
Okay.
So,
Like my question was like, how is the relation between the potential energy surface and that specific geometry that is changing? I don't know. It's
well, this is at this point here.
uh-huh.
At this point here, the configuration looks like this. So this is the excited state, electronic excited state, the first electronic excited state, singlet state. It looks like this at this point. It's come out of the plane. Okay, so that lowers the potential energy. Okay, and we have the vibrational states, which are degenerate of that excited state with the vibrational states of the ground state. So then at this point, the energy can go from the electronic excited state to the electronic ground state through vibrations. If you like, I can send you some more literature on conical intersections.
Okay, please.
Okay. So what are some of the advantages of photochemical reactions over thermal reactions? Well, for thermal reactions, we have an energy available in the solvent, let's say the molecule in a solvent, which goes basically as K, Boltzmann constant, times temperature. But sometimes we have, for example, between different configurations of the molecules or different products, we have a very large activation energy. And the energy available in the solvent due to the temperature, so the temperature is the vibrational motion, the rotation and translation, the molecules, overall, this is the average energy over all the degrees of freedom, which depends on the temperature. This energy is not enough to go over the barrier. So we basically stay, if we have a large potential energy barrier between the two different forms, we stay in one configuration. But if and the probability is going as something like an exponential, no? So if the activation energy becomes very large, then the probability goes down very fast, exponentially fast with activation energy. But if we have a photon, then in a single photon, we have enough energy to get over this energy barrier. So as an example, the energy of a mole of photons, 6.023 times 10 to the 23 photons at 254 nanometers is 190 times more than KT. So we have much more free energy to be able to go over this barrier. So that's one of the advantages of photochemical reactions over thermal reactions. We can do many more transformations because we're not limited by the activation energy barrier. So that's comparison is at 25 degrees centigrade. So that's comparing to the energy, KT, available at 25 degrees centigrade. So therefore, we can do things like isomerizations, tautomerizations, rotations around bonds, single or double bonds, charge transfer, substitutions, exciplex formation, and whatever other molecular reconfiguration. Now, as I mentioned, even though the probability is small, like 1 in 1,000, we can excite the system to a triplet state. And with the system in a triplet state, it's a long-lived state, so we can have new reactions. For example, if we could excite the DNA molecule into the triplet state, then the energy, if it was absorbed by one base, has a possibility of distributing itself over many bases, because the triplet state is a long-lived state. But if it goes, if it's not excited to the triplet state, only to the singlet state, then the energy would go very rapidly just to that base into the water, 10 to the minus 12 seconds. So there's no time for new reactions to occur. But in the triplet state, new reactions could occur, or we could get phosphorescence. which is the emission of a photon after a period of time, which could be up to seconds or to even hours in some molecules. Now, if we're also, another advantage of these photochemical reactions that we can have energy transfer from one molecule to another, which normally could not happen in thermal reactions, because the energy which is given to a molecule is only very small energy due to the thermal motion, the collisions with the other molecules in the system. But if we excite the molecule through a photon, then we could have a large energy, and that energy can be transferred to another molecule. For example, it could go from tryptophan to DNA, which has a conical intersection. Tryptophan doesn't have a conical intersection, but if tryptophan is close enough to DNA, then we can have an energy transfer, a large energy transfer from tryptophan to the DNA molecule. So there are a number of advantages for photochemical reactions over thermal reactions. Essentially, the most important is that we have a large amount of energy because of the large amount of energy contained within a photon, and that allows us to access many more different configurations, changes to the molecules. So an example then, this is the production of adenine from 5 molecules of hydrogen cyanide. So this configuration, which is known as cis-DAM, is basically the lowest free energy, the Gibbs free energy, that it means a constant temperature and pressure of 4 molecules of hydrogen cyanide, that it gives this cis-DAM configuration. Now, this absorbs photons at 298 nanometers. So that corresponds to here on the graph of the UVC light coming in at the Earth's surface. There's not much light, it's not zero, but there is some light. And if it absorbs at that wavelength, that's where the maximum is. So there's a broad range, but this is the maximum, 298 nanometers. Then we can have a rotation around this double bond. Okay, so this is known as trans-DAM. And that is absorbing at 3. I can't see on the graph where 3 is, but that corresponds to 313 nanometers, which should be here, okay, about here. And then by absorbing this photon at 313 nanometers, we can have a proton transfer. So we have a transfer of one of these hydrogen atoms to this nitrogen. So that gives us this reconfiguration. And then by absorbing at 275 nanometers, which is about here, we can form a ring structure here. And then we have a couple more chemical reactions which occur through temperature. And finally, we get to AICN and adenine, and they're absorbing at the maximum. For example, adenine absorbs at 260 right here at the maximum. In AICN at 250, where there is more light than at 275, for example. So the advantage of the photon is that we can go over these activation energy barriers. For example, this rotation around the double bond requires photon of wavelength at least 298 nanometers, which we could not do at temperatures. Only at very, very high temperatures, thousands of degrees, that may happen. We might get a probability which is non-zero for trans-DAM. But through absorbing photons with the molecule at normal lab temperature, normal temperatures, let's say 25 degrees centigrade, we can have these cis-DAM to trans-DAM and all these other photochemical reactions occurring. So what about the evolution of the system? Okay. So we're taking only the first step in this reaction, 2 going to 3. So cis-DAM going to trans-DAM. And as we mentioned, they have different wavelengths of maximum absorption. So depending on the intensity of the light at those wavelengths of maximum absorption, we really have to do an integral, over the absorption spectrum for the different molecules. But to make it less complicated, let's just look at the maximum absorption, wavelength of maximum absorption, and the intensity at the wavelength of maximum absorption for cis-DAM. This is this here, cis. And also, this is the product molecule that is after the absorption of the photon, which is trans-DAM. We also have to look at its intensity of the light arriving at the surface and at its wavelength of maximum absorption of trans-DAM. So this gives us a probability for going in the forward direction and for going in the backwards direction. And you know, in equilibrium thermodynamics, the two efficiencies are equal. So we don't get any change in the concentrations. But in the case of, for example, absorption of a photon, well, we can also have what were known as these internal conversion, where we absorb the photon, and instead of going to a product molecule, we go to the ground state through internal conversion very rapidly. That is through the conical intersection to the ground state. So that depends then on the conical intersection for quenching to the ground state or dissipation to the ground state. And the same for the case of trans-DAM. So we have different quantum efficiencies for this dissipation to the ground state through the internal conversion. So you can convince yourself that in order to get a transition from this molecule to this molecule, we have to have that this is greater than this, okay, where these are the quantum efficiencies. Well, I guess I have only 10 minutes left, so I'm going to try to hurry. But so this is the quantum efficiency for this chemical or transformation. This is a rotation around the double bond, this QF in the forward direction. And this QB is for the transformation in the backward direction. So you can convince yourself that if we have that this is greater than this, then the system will automatically go, will be more probable to go to the forward direction. So we go on this path here to the forward direction, always the forward direction. And you can see that to make this smaller, the following molecule always smaller, we need a greater quantum efficiency for dissipation to the ground state through internal conversion. Internal conversion, that's why QIC. So that allows us to go through an evolutionary process. So the system will naturally go through an evolutionary process to form a molecule, which is adenine, which has such a large quantum efficiency for internal conversion to the ground state, that it's the smallest possible of all the possible molecules with that configurations, with those atoms. So we finally arrive at adenine, which is very stable, and so there's no chemical reactions taking it to another state, because whenever it absorbs a photon, almost immediately it goes to the ground state through the quantum efficiency for internal conversion. So that's why we're left with adenine. So this is the evolutionary process through dissipation, which is taking us from simple molecules to rather complex molecules, which of course would not happen in equilibrium. Okay, we need a non-equilibrium system corresponding to ultraviolet light imposed over the system for the evolution in this sense. So this is the very basic, maybe the first steps in evolution. Now we can always go then up farther and farther up to the biosphere. Of course, it becomes much more complex and difficult to describe, but basically the same process is happening. We're going from one system which is less dissipating to systems which are more and more dissipated. Okay, so let me just go quickly through the homework, and then if there's any questions and we still have time, we can discuss. Okay, so homework number 4 is to find an organic molecule that has a conical intersection through internal conversion to its ground state. So if you want to find one quickly, just look at the fundamental molecules, those molecules which are in the 3 domains of life. And I have plotted those molecules on the spectrum of the UVC light arriving at Earth's surface. So if you want, just take one of those molecules off there, not one that we have already covered, like adenine or guanine. Well, maybe you can even do guanine, Claudette, since you are working on it. Why not? No, look at the conical intersection of guanine, and the others take different molecules and discuss the photochemical details of the molecule. So the wavelength of absorption, the width of transition, the excited state lifetimes, etc. And how the molecule deforms in its excited state to reach this conical intersection, which allows it to dissipate very quickly to the ground state. Okay, so that's find a molecule of your choice, preferably one which is one of the fundamental molecules of life, a molecule at least related with life, and discuss the photochemical details of the molecule and how it deforms to go to the excited state to reach its conical intersection. And number 2 of the homework is to discuss in detail 2 distinct photochemical reactions that occur today in living organisms. And I've just given you some examples. There's a lot more, and you can choose whichever one you like, but take 2 distinct examples. For example, the production of vitamin D. We know that we need ultraviolet light to produce vitamin D in our bodies. We need sunlight. Vision is also another photochemical reaction. Phototaxis is where bacteria are attracted to light. So they know their way up. For example, if they're in the ocean surface, they can find the surface quickly. So they're attracted to light. So these are different photochemical reactions which occur today in living organisms. So just to discuss in as much detail as you can these photochemical reactions which occur. Okay, so we have about 5 minutes for any questions. Are there any questions first about the homework? Nobody has any questions? You're still there?
¿Cuándo se entrega, Doc? Perdón.
In 2 weeks.
2 weeks.
2 weeks.
Thanks.
And please, if you haven't done the previous homeworks, 1, 2, and 3, please do them and send me a copy, as well as send Roberto, who's the helper, okay? El asistente, Roberto. Ahí encuentras su email en mi lista, ¿no?
I have a question. It says that we have to find an organic molecule that has a conical intersection.
Yes.
We could just like investigate it, or we have to demonstrate that it has a conical intersection. I don't know, or it's just the investigation.
Yeah, just investigate in the literature, because the experiments are very complicated. Esmeralda, right?
Okay. Yeah.
Yeah, they are very difficult experiments to do. You need very sophisticated apparatus, which we don't have. So just to investigate in the literature, a lot has been published. A lot has been published. It's becoming very, how do you say, very popular, conical intersections now, because they're finally beginning to understand them and realizing that it has a lot to do with photochemical processes. But they still haven't realized, at least as far as I'm aware, that I'm the only one who's showing that these conical intersections are very related with evolution of the system, no? And for this case, going from different configurations of molecules, we need a conical intersection to the ground state, which is very large, so it goes in this direction. It goes in the forward direction. Okay?
Okay.
So
yeah, thank you.
Just look in the literature for a particular molecule and which has a conical intersection. Not all of them do, to the ground state. Okay, for internal conversion, that's very quickly dissipating the energy. Okay, so are there any questions, further questions in the homework or about what we discussed today? We still have a couple of minutes for anyone. Is this slide understandable? It may be a little complex if it's the first time you've looked at it. But the probabilities of going in the forward direction, of course, depend on the intensities of the light, because we need the light to go in the forward direction to be absorbed here before we can get over the activation barrier. And it depends on the quantum efficiency for going in the forward direction. So these quantum efficiencies must add up to 1. So there can be different reactions occurring. Now we can have also maybe hydrolysis. That means the addition of a water molecule to the molecule. So there could be many different reactions, but this reaction is what we're interested in. So this has the quantum efficiency QF. So as long as this is small and this is large, then we're going in the forward direction. Try to understand this, look at this, because this is basically the principle of evolution in physical chemical terms, which I don't think anybody has seen before. Okay, are there any further questions or comments?
I think everything's fine. I think.
Sorry?
Just for the moment.
No, Claudia?
I think that later I'm going to have more questions.
Okay.
Later.
Well, you can also write me an email, everybody.
Oh yeah, can you send me like information about the quantum state that we saw, and also this
You mean-
diagram,
yeah.
because I'm
You mean
I'm
the
little.
quantum selection rules? Esmeralda, sorry, you have to specify in more detail. You mean the quantum selection rules?
Yeah, quantum
Okay.
selection,
Yes,
because
yes,
I've only take what introducción a la física cuántica.
Okay, okay.
Yeah.
Yes, I'll send it